Let's do another Newton's laws of motion problem. This is the cart with two hanging masses. Let's call this the forward direction, that way the backward direction. All three masses are connected and they will all have the same acceleration. So we'll find the acceleration of the entire system first. That's a force forward. That's a force backward. The weight of the cart and the normal force, they'll cancel out, so I won't bother with them. Those two tensions are internal to the system. Those two tensions are internal to the system. They'll all cancel out. So I take the sum of the external forces equals the mass of the system times the acceleration. All three have the same acceleration. Forces forward minus forces backward. Mass of the system, acceleration of the system. A little algebra, and you got your answer. So keep in mind, this is the net force that's making the system accelerate. This represents the inertia of the whole system. Let's practice with these masses. 8 kilograms times 9.8. 2 kilograms times 9.8. F equals ma. Remember, we're doing the whole system. The force forward minus the force backward. 15 kilograms for the system times a. We get 3.92 meters per second squared. Now that's the acceleration of each one of these items. Remember that now. Let's go calculate this tension too, pulling back on that 8 kilograms. If I isolate this object, that now becomes an external force. Whereas before it was internal to the system, all those other tensions were internal too. Always start out with F equals ma, forces forward, minus that force pulling this guy back, equals 8 kilograms times the acceleration, and they're all the same. And now we can solve for t. And there we have it, 47.04 newtons. And that tension is smaller than this force, and that seems right because it's accelerating in this direction. Let's isolate this object and calculate T3. F equals ma. Now look closely at this. That's the forward force. That's going backward. So that's why that's here first. This acceleration is put in as a positive value because we've said that this entire direction is positive. 27.44 newtons. And that number is now bigger than this number, and that makes sense because it's got to accelerate in that direction. Just to double check the work, let's isolate the cart and see what we get with T2 and T3. As we saw before, T2 and T2 here have to be the same going over a frictionless massless pulley. Same thing over here. That's the forward force, that's the backward force, and that's the mass of this system. Isn't that great? It checks out. We still get the same acceleration. Let's finish with one more great question. How much mass would you have to add to the cart to cut the acceleration in half? We're going back to the beginning. The sum of the forces, that's not going to change. Those masses aren't allowed to change in this problem. So what's the mass of the system? It's 15 kilograms. Well then, times A. So if this stays the same, what would I have to do to this number to make that get cut in half? I'd have to make it 30 kilograms. I've got to double the mass of the system. But I'm not allowed to change these because the problem says how much mass would I have to add to the cart? I've got to add 15 kilograms to get the mass up to 30. And the only place I can add it is to the cart. So it's 15 is what I got to add to it. And just the last word about the pulleys and the way we're setting this thing up. If a pulley only changes the direction of the force internally, we could redraw the diagram and make it look like this, as if we have 3 boxes tied together with strings and we're pulling them in space. There's a force forward and a force backwards. You'll get the same results. Good luck, everybody.